Aberdeen Proving Ground, Maryland, July 1945. The summer heat shimmered off the Tiger II's massive hull as it sat motionless on the testing grounds of Aberdeen Proving Ground. At 68.5 tons, it was the heaviest operational tank of World War II, a monument to German engineering ambition. Its 88 kW K-43L-71 gun could penetrate any Allied tank from ranges exceeding 2,000 meters. Its frontal armor, up to 185 millimeters thick, had proven virtually immune to Allied tank fire at combat distances. German propaganda had proclaimed it invincible, the ultimate expression of armored warfare. Captain Richard Morrison of the U.S. Army Ordnance Department stood in the blazing Maryland sun, studying the captured behemoth with a mixture of professional curiosity and practical skepticism. His team had spent weeks arranging the Tiger II's transport from the port of embarkation to Aberdeen. The logistics alone had been revealing. The tank was too heavy for standard rail cars and required specialized heavy-duty transport that only a handful of facilities possessed. Morrison's assignment was straightforward. Evaluate this fearsome weapon, understand its capabilities, identify its vulnerabilities, and determine what lessons American tank development should learn from it. What he and his team discovered over the following months would fundamentally reshape American understanding of armored vehicle design, revealing that the most powerful tank of the war was also one of its most impractical. The bridge problem emerged on day one. Before Morrison's team could begin comprehensive ballistic testing, ordnance testing, or mechanical evaluation, they needed to move the Tiger II between various facilities at Aberdeen. The proving ground covered more than 72,000 acres and included specialized ranges for different types of testing: armor penetration ranges, automotive test tracks, durability courses, and mechanical evaluation facilities. This routine logistics requirement immediately exposed the Tiger II's fundamental flaw. Lieutenant James Kowalski, the motor pool officer assigned to support the testing program, examined bridge capacity charts with growing disbelief. "Sir," he reported to Morrison, "we have a problem. The Tiger can't cross 3/4 of the bridges on this base without engineering assessment and reinforcement." At 68.5 tons combat-loaded, the Tiger II exceeded the weight capacity of virtually every bridge designed for standard vehicular traffic. American military bridges were typically rated for Class 40 loads, roughly 40 tons, or Class 60 loads, roughly 60 tons. The Tiger II required Class 70 capacity, a classification that barely existed outside of major commercial spans. Morrison requested detailed maps of bridge capacities throughout Maryland. The results were sobering. The Tiger II could not safely cross the majority of bridges in the state without risk of structural failure. This wasn't a Maryland-specific problem. It was universal. Bridge engineers estimated that approximately 70–80% of bridges in Western Europe, where the Tiger II was designed to operate, could not support its weight. "Pull the operational records for German Tiger II units," Morrison ordered. "I want to know how they dealt with this." The captured documents told a revealing story. Every German heavy tank battalion equipped with Tiger IIs required extensive advance reconnaissance not primarily for enemy positions, but for route planning. Engineers had to survey every bridge along proposed routes of advance, calculate load capacities, and either find alternatives or bring up bridging equipment. In some cases, Tiger IIs had to ford rivers because nearby bridges couldn't support them. One German after-action report from the Ardennes offensive was particularly illustrative. Shear Panzerabteilung 506 had been assigned a specific axis of advance, but had to abandon the planned route entirely when reconnaissance revealed that 4 consecutive bridges along the route were inadequate. The battalion's advance was delayed by more than 12 hours while engineers found alternative routes, and by the time the Tigers reached their intended positions, American reinforcements had arrived. Compare this to American operational planning. The M4 Sherman weighed between 30 and 35 tons depending on variant. The M26 Pershing, America's heavy tank response, weighed 46 tons. Both could cross virtually any bridge rated for commercial traffic. Morrison's team consulted with combat engineers who had served in Europe. "We never worried about bridge capacity with Shermans," one major explained. "If civilian trucks could cross it, Shermans could cross it. We worried about bridge capacity when moving our tank destroyers and heavy equipment, but standard tanks, never an issue." The Tiger II turned this assumption upside down. It couldn't go where trucks could go. It couldn't take routes that medium tanks could take. Every movement required engineering assessment, and in the fluid, mobile warfare of 1944-1945, this was catastrophic. Morrison's team conducted systematic testing. They identified every bridge within the Aberdeen testing area and classified them by capacity. Then they simulated operational scenarios, emergency redeployment, rapid advance, tactical withdrawal, and tracked how bridge capacity affected options. In scenario after scenario, the Tiger II's weight eliminated viable routes that lighter tanks could use. The tactical implications are profound, Morrison wrote in an interim report. A tank that cannot maneuver strategically, regardless of its combat capabilities, has severely limited operational value. The Tiger II can win any engagement it reaches, but reaching engagements is itself a significant challenge. Once mobility testing was complete, Morrison's team began detailed mechanical evaluation. They had three objectives: understand the Tiger II's engineering, identify potential vulnerabilities, and assess reliability under operational conditions. The Maybach HL230P30 engine produced an impressive 700 horsepower at 3,000 RPM, a powerful engine by 1945 standards. German engineers had selected it as the only available power plant capable of moving 68 tons. But raw horsepower told only part of the story. Power-to-weight ratio determined actual performance. The Tiger II's 700 horsepower had to move 68.5 tons, yielding approximately 10.2 horsepower per ton. The Sherman, with 400-500 horsepower, depending on variant, moving 30-35 tons, achieved 12-14 horsepower per ton. Despite having a less powerful engine, the Sherman actually had superior power-to-weight performance. The practical effects were measurable. On level roads, the Tiger II could reach a maximum speed of 41.5 kilometers per hour, 26 mph, respectable for a heavy tank. But maximum speed meant nothing in combat conditions. On test tracks simulating European terrain, mud, hills, rough ground, the Tiger II's speed dropped dramatically. Cross-country speed averaged 15-20 kilometers per hour. The Sherman, on identical terrain, maintained 24-30 kilometers per hour. Speed isn't everything, one of Morrison's analysts noted, but in mobile warfare, it's close to everything. A tank that arrives 12 hours late to a critical position might as well not exist. Fuel consumption proved even more problematic. The Tiger II carried 860 liters of fuel in its internal tanks. Under ideal conditions, paved roads, moderate speed, no combat operations, this provided approximately 120 kilometers of range. Morrison's team calculated that under combat conditions, range dropped to 80-90 kilometers. They ran fuel consumption tests under various conditions. Highway cruise, 7.2 liters per kilometer. Cross-country, 9.5 liters per kilometer. Combat operations, frequent acceleration, turret traverse, extended idling, 11-12 liters per kilometer. The numbers were shocking. A Tiger II battalion conducting a 100-kilometer advance required more fuel than an entire Sherman regiment covering the same distance. Morrison requested comparative analysis from units that had fought in Europe. One logistics officer provided detailed figures. A Sherman company, 14 tanks, consumed approximately 2,500 gallons of fuel daily during active operations. A Tiger II company of equivalent size would require roughly 4,500 gallons daily. That's 80% more fuel for fewer operational tanks, since Tiger IIs had lower mechanical readiness rates. The transmission became the focus of intense scrutiny. The Maybach OLVAR OG401216B transmission was a sophisticated piece of engineering, 8 forward gears, 4 reverse gears, hydraulically operated. It had been designed for the Panther, which weighed approximately 50 tons. The Tiger II's additional 18 tons stressed it beyond design specifications. During testing, the transmission failed. Completely. The Tiger II was conducting standard mobility trials when the transmission seized. Morrison's mechanics spent 3 days disassembling it to determine the cause. They found multiple gear teeth sheared, hydraulic seals blown, and bearing surfaces scored. "How common is this?" Morrison asked, examining the damaged components. They consulted captured German maintenance records. The data was damning. Average transmission life in Tiger IIs was approximately 150 kilometers before requiring major service or replacement. Some units reported transmission failures occurring every 100 kilometers. By comparison, Sherman transmissions typically lasted 2,300 kilometers before requiring overhaul. The replacement process was itself revealing. Changing a Tiger II transmission in field conditions required approximately 20 man-hours with specialized equipment. If specialized equipment wasn't available, the time extended to 40-50 man-hours. Sherman transmissions could be changed in 10-12 man-hours with basic maintenance equipment that every tank unit carried. This isn't just a reliability issue, Morrison observed. It's an operational availability issue. Time spent in maintenance is time not spent in combat. The Tiger II's running gear attracted particular attention from American engineers. The tank used an overlapping, interleaved road wheel system, 9 sets of wheels on each side, arranged in overlapping pairs. This design distributed the tank's enormous weight more evenly across the track, reducing ground pressure. In theory, the system was brilliant. In practice, it created multiple problems. Morrison's team conducted cold weather testing using industrial freezers to simulate European winter conditions. They packed mud around the wheels, soaked the running gear with water, and then froze everything to -15 degrees C, 5 degrees F. The results confirmed reports from captured German crews. The overlapping wheels trapped mud, snow, and debris. When temperatures dropped below freezing, this material froze solid, completely immobilizing the wheels. German field reports described crews using blowtorches, picks, and even explosives to free frozen wheels before operations. One captured maintenance officer reported instances where Tigers sat immobilized for 6-8 hours while crews worked to free frozen running gear. "We experienced this with the first winter in Russia," the German officer explained during interrogation. "The interleaved wheels trapped everything. We tried various solutions, fewer wheels, rubber protectors, different spacing, but the basic design was flawed. The problem never went away." Even worse was maintenance. The overlapping design meant that replacing a damaged inner wheel required removing up to 8 outer wheels first. Morrison's team timed this process repeatedly. Replacing an outer wheel took approximately 1.5 hours. Replacing an inner wheel took 6-8 hours because of the sequential disassembly required. Sherman wheels, by contrast, were independently mounted. Each wheel could be accessed and replaced without disturbing others. Average replacement time, 45 minutes per wheel. "Imagine a combat scenario," Morrison noted in his report. "A Tiger II takes minor track damage requiring one wheel replacement. If it's an outer wheel, the tank is out of action for 2 hours minimum. If it's an inner wheel, the tank is immobilized for most of a day. The same damage to a Sherman means 45 minutes out of action. The operational implications are obvious." Ballistic testing began in August 1945. Morrison's team had acquired a comprehensive array of anti-tank weapons for evaluation. American 76mm guns, British 17-pounders, Soviet 85mm and 122mm guns, and captured German weapons for baseline comparison. The Tiger II's armor scheme was formidable on paper. Frontal hull armor, 150 mm at 50 degrees from vertical, effective thickness of approximately 235 mm. Turret front, 185 mm at 10 degrees, effective thickness of approximately 220 mm. Side armor, 80 mm. Rear armor, 80 mm. Testing confirmed what combat reports had indicated. The Tiger II's frontal armor was essentially immune to most Allied tank guns at typical combat ranges. The American 76mm gun, firing standard AP ammunition, could not penetrate the frontal armor at any range. Even the British 17-pounder, one of the war's most powerful anti-tank guns, struggled against the Tiger II's frontal protection at ranges beyond 500 meters. "This is impressive," Morrison acknowledged, watching test rounds ricochet off the glacis plate. "But let's talk about costs." The armor thickness created multiple problems. First was weight. The turret alone weighed 11.1 tons, more than many light tanks. This necessitated powered traverse because the turret was too heavy for manual operation in combat conditions. The traverse motor, however, proved fragile and failed during testing. Mechanical engineer Lieutenant Sarah Patterson examined the failed motor. "The design is adequate for the turret weight," she explained, "but barely. There's no redundancy, no safety margin. When the motor fails, and it will fail under combat stress, the crew has to traverse manually. They tested manual traverse. A full 360-degree rotation required approximately 2 minutes of continuous hand cranking by 2 crew members. For reference, a Sherman could complete 360 degrees of turret traverse in 15 seconds using powered traverse, or about 60 seconds manually. In combat, this means the Tiger II can't respond quickly to threats from different directions, Patterson noted. If engaged from multiple angles, the crew must decide which threat to address, knowing they can't quickly shift to engage others. The armor quality itself became a research focus. Morrison's team tested the armor with various ammunition types and documented hardness, composition, and performance. They found significant variation in armor quality, particularly in late production plates. Analysis revealed why. By 1944, Germany's access to alloying materials, manganese, nickel, molybdenum, was severely restricted. These materials were essential for producing high-quality armor steel. Without them, German metallurgists compensated by increasing carbon content and heat treatment, but this made armor more brittle. Tests showed that late-war Tiger II armor, while thick, was prone to spalling and cracking even when not penetrated. High-velocity impacts that didn't breach the armor could still create dangerous spalling on the interior surface, fragments of metal that killed or injured crew members. Earlier German armor, with proper alloying, performed better. The irony, Morrison wrote, is that Germany's industrial situation forced them to compensate for declining armor quality by increasing armor thickness, which increased weight, which degraded mobility and reliability. It's a vicious cycle driven by strategic resource limitations. In September 1945, Morrison's team received comprehensive German production records captured from Henschel und Sohn in Kassel, the Tiger II's primary manufacturer. The documents revealed the staggering industrial challenge of producing such a complex vehicle. Each Tiger II required approximately 300,000 man-hours to manufacture from start to finish. This included fabrication of individual components, subassembly, final assembly, and testing. For comparison, a Sherman required approximately 7,500 man-hours. Morrison arranged the numbers in a table that made the disparity clear. Tiger II, 300,000 man-hours per vehicle Sherman, 7,500 man-hours per vehicle ratio. One Tiger II required 40 times more labor than one Sherman. The implications were profound. In the time required to build one Tiger II, American factories could produce 40 Shermans. Even accounting for quality differences and combat effectiveness, this ratio was catastrophic from a strategic perspective. Production numbers confirmed this. Germany manufactured 489 Tiger IIs during the entire production run from January 1944 to March 1945. In that same period, roughly 14 months, American factories produced approximately 21,000 Shermans. Soviet factories produced roughly 19,000 T-34s. Britain produced approximately 2,800 Cromwells and Churchills. The mathematics are unambiguous, Morrison noted. Germany allocated resources to produce 489 tanks that were individually superior but collectively insufficient. The Allies produced tens of thousands of tanks that were individually inferior but collectively overwhelming. Cost analysis reinforced this conclusion. German financial records indicated each Tiger II cost approximately 800,000 Reichsmarks to produce. A Panther cost 343,000 Reichsmarks. A Panzer IV cost 115,000 Reichsmarks. A Sherman cost approximately $44,500, roughly 180,000 Reichsmarks at wartime exchange rates. Morrison's team interviewed a captured German procurement officer, Oberst Friedrich Hartmann, who had been involved in armored vehicle acquisition for the Wehrmacht. "We knew the numbers didn't favor us," Hartmann admitted. "We knew the Allies could outproduce us by ratios of 20, 1, 30, 1, even higher in some categories. The Tiger II was designed under the assumption that qualitative superiority could overcome quantitative inferiority. A single Tiger II, theoretically, could engage and destroy multiple enemy tanks before being disabled." "And did it work?" Morrison asked. Hartmann was silent for a moment. In individual engagements, yes, Tiger IIs achieved impressive kill ratios when they reached combat and when they had fuel and ammunition. but they rarely reached combat at full strength. They broke down en route. They ran out of fuel. They were abandoned during retreats, and there were never enough of them. You could position a Tiger II company at a critical point, and they might hold that point successfully, but you couldn't be at every critical point simultaneously. Your Shermans were everywhere. Our Tigers were somewhere. October 1945 brought Morrison's team to what many considered the most important aspect of tank evaluation: sustained operational readiness. How reliable was the Tiger II? How maintainable? What were the logistics requirements? They established a rigorous testing protocol. The Tiger II would undergo simulated operational use, daily movements, mock combat exercises, terrain trials for 30 consecutive days. All maintenance would be documented: hours required, tools needed, parts replaced, problems encountered. The results were sobering. Over 30 days of moderate use, far less intensive than actual combat operations, the Tiger II required 847 man-hours of maintenance. This included track adjustments and replacements, 142 hours. Engine maintenance, 196 hours. Transmission service, 183 hours. Suspension and running gear, 167 hours. Electrical and hydraulic systems, 89 hours. Turret and gun systems, 70 hours. For comparison, they ran the same protocol with a Sherman. It required 131 man-hours of maintenance over the same 30-day period. Master Sergeant Robert Chen, the senior mechanic on Morrison's team, provided perspective. In a combat environment, you have limited maintenance time. Tanks need to be ready to move, often on short notice. The Sherman requires basic daily maintenance, fluid checks, track tension, lubrication. That takes maybe 45 minutes with a full crew. The Tiger II's daily maintenance takes 2-3 hours minimum. That's time your tank isn't available for operations. Parts commonality became another focus area. Chen's team cataloged every component in both tanks and identified which parts were shared with other vehicles. The Sherman shared components with numerous other American vehicles. The engine was used in various configurations across multiple military vehicles. The transmission was similar to commercial truck units with military modifications. Radio equipment was standard across the vehicle fleet. The 75 and 76 guns used the same ammunition as tank destroyers and some towed artillery. The Tiger II shared virtually nothing with any other German vehicle. The Maybach HL-230 engine was specific to the Tiger II and Panther, but different transmission configurations meant parts weren't fully interchangeable. The transmission was unique to the Tiger II. The gun was unique to the Tiger II. Even small components, specific bolts, seals, electrical switches, were custom manufactured. This creates a nightmare supply chain, Chen explained. Every Tiger II unit needs its own specific supply pipeline. You can't cannibalize parts from other vehicles. You can't substitute components. If a Tiger II needs a specific part and that part isn't available, the tank is deadlined until the part arrives. They tested this empirically. They simulated field damage, disabled a track, removed engine components, damaged the gun breech, and timed how long it took to return the vehicle to operational status using only parts available at Aberdeen. For the Sherman, most repairs were completed within hours using standard parts inventory. For the Tiger II, they had to order specific parts from specialized suppliers. Several repairs took weeks because the required components weren't available anywhere in the United States and had to be fabricated specially. German logistics documents captured after the war confirmed this was a persistent problem. Schwer Panzerabteilung 503, operating in Hungary in early 1945, reported that at any given time, 40–60% of its Tiger IIs were non-operational awaiting parts. Some tanks sat immobilized for weeks because a single specialized component wasn't available. The tragedy, Morrison wrote, is that many of these were minor failures, a damaged final drive, a broken steering mechanism, issues that would take hours to repair if parts were available. But the parts weren't available, so the tanks sat idle or were eventually destroyed to prevent capture. Morrison's team recognized that mechanical evaluation told only part of the story. They needed to understand the Tiger II from the crew's perspective. Over the next several months, they interviewed dozens of captured German tank crews who had operated Tiger IIs in combat. Hauptmann Klaus Weber, formerly the commander of 2nd Company, Shear Panzerabteilung 503, provided detailed testimony. His unit had received Tiger IIs in August 1944 and operated them until the unit's destruction in March 1945. The Tiger II was both our greatest asset and our greatest liability, Weber explained. When it worked, when we had fuel, when we could position it properly, it was magnificent. We could engage enemy tanks from ranges where they couldn't effectively return fire. I personally witnessed Tiger IIs destroying 7, 8, even 10 enemy tanks in single engagements without taking penetrating hits. But, Morrison prompted. But those engagements were rare. Most of our time was spent managing the tank's limitations. Fuel was constantly problematic. We received perhaps 60% of our allocated fuel supplies, and the Tiger II consumed it voraciously. Route planning was a constant nightmare. I spent hours studying maps, not for tactical advantage, but to find routes our tanks could actually traverse. Weber described the Ardennes offensive from his perspective. His company started with 6 operational Tiger IIs. 1 broke down before reaching the start line, transmission failure. 2 more suffered mechanical failures during the advance, blocking narrow forest roads and creating traffic jams. Of the 3 that reached their intended positions, 1 ran out of fuel and was abandoned. The remaining 2 fought well, destroying multiple American vehicles, but eventually both were destroyed during withdrawal. 1 by its own crew when fuel ran out, the other by American aircraft. We started with 6 tanks, Weber said. We lost 2 to mechanical failure, 2 to fuel starvation, and 2 to enemy action. That ratio, 4 lost to our own limitations, 2 lost to the enemy, was typical. Unteroffizier Hans Brandt, a Tiger II gunner, provided perspective from inside the turret. The gun was extraordinary. The optics were excellent. At ranges of 1,500 to 2,000 meters, we could identify and engage targets with confidence. I hit enemy tanks at ranges they couldn't even see us. What were the downsides? Morrison asked. The turret traverse, Brandt replied immediately. When the motor worked, it was slow but acceptable. But the motor failed frequently, and manual traverse was impossibly slow. In one engagement, we were ambushed from multiple directions. We engaged threats to our front, but while we were traversing to engage threats from our left flank, we were hit from the right by a tank we couldn't turn to face quickly enough. Brandt also noted crew fatigue. The Tiger II was physically demanding to operate. Everything was heavy, hard to manipulate. After 8 or 10 hours inside, you were exhausted in ways that you weren't in a Panzer IV. This might seem minor, but crew fatigue affects performance. Tired crews make mistakes. Feldwebel Otto Klein, a Tiger II driver, focused on the mechanical challenges. The Tiger II required constant attention. You couldn't just drive it, you had to actively manage it. The transmission needed careful gear selection. The engine overheated if you pushed it too hard. The steering was heavy and required anticipation. Klein described an incident near Budapest. His Tiger II was conducting a tactical withdrawal when the engine overheated. We stopped to let it cool. Standard procedure, you learn not to push the engine past certain temperatures, but while we waited, the tactical situation changed. Other units had already withdrawn, and we were suddenly isolated. We eventually got the engine cooled and operational, but by then we were behind enemy lines. We spent 2 days infiltrating back to German positions. An entire tank crew moving on foot because our tank couldn't be pushed hard without overheating. In November 1945, Morrison expanded his evaluation to include detailed fuel consumption analysis. Working with petroleum engineers from the Army's Quartermaster Corps, they conducted comprehensive testing under various operational scenarios. The baseline was established through controlled testing, 7.2 liters per kilometer on paved roads at cruising speed. But baseline figures meant nothing in combat conditions. They established more realistic scenarios. Combat approach march, movement to contact, moderate speed, varied terrain. 9.1 liters/km defensive positioning, frequent short movements, extended idling. 11.3 liters/km. Active combat, rapid maneuvering, frequent acceleration, gun operation. 12.4 liters/km pursuit or withdrawal, maximum speed, aggressive driving. 13.8 liters/km. With an 860-liter fuel capacity, this meant cruising range, 120 km. Combat approach, 94 km. Defensive operations, 76 km. Active combat, 69 km. Pursuit withdrawal, 62 km. Morrison's team obtained German operational logs from various Tiger II units and cross-referenced them with these figures. The correlation was striking. Units consistently reported achieving 60-80 kilometers between refueling during active operations, exactly matching the test predictions. They compared this to the Sherman. The M4A3 Sherman carried 590 liters of fuel and consumed approximately 2.4 liters/km under combat conditions. Combat range, approximately 245 kilometers, more than 3 times the Tiger II's practical range. The strategic implications are profound, Morrison wrote. A Sherman company can operate 200-plus kilometers from its fuel supply point and still maintain combat effectiveness. A Tiger II company must remain within 60-70 kilometers of reliable fuel supply. This constrains not just individual operations, but entire campaign planning. He interviewed German logistics officers captured during the war's final months. Major Heinrich Schmidt, who had been responsible for fuel allocation for an entire Panzer Corps, provided revealing testimony. By late 1944, Germany's fuel situation was desperate, Schmidt explained. Synthetic fuel production was being disrupted by Allied bombing. Romanian oil fields were lost. Distribution was disrupted by air attacks and partisan activity. We allocated fuel based on strategic priorities, and Tiger II units received relatively high allocations, but it was never enough. Schmidt provided specific figures. A Tiger II battalion at full strength, 45 tanks, required approximately 500,000 liters of fuel per month to maintain reasonable operational tempo. We typically receive 250,300,000 liters monthly. Units learned to operate under chronic fuel shortage. Tanks sat immobile, waiting for fuel trucks that might or might not arrive. The human cost of fuel shortages appeared in unit histories. Schwer Panzerabteilung 501, operating in East Prussia in January 1945, lost 23 Tiger IIs during a Soviet offensive. Investigation revealed only 4 were destroyed by enemy fire. 12 were abandoned due to fuel exhaustion. 7 were destroyed by their own crews to prevent capture when fuel for withdrawal wasn't available. The ultimate weapon, Morrison observed, is only ultimate when it has fuel. Without fuel, the Tiger II is 68 tons of immobile metal. Oberstleutnant Friedrich Steiner had been an intelligence officer assigned to assess Allied armored capabilities. Captured in April 1945, he was initially reluctant to discuss his work. Morrison eventually convinced him that the war was over, and that honest technical discussion served no strategic purpose for either side. Steiner's testimony provided crucial perspective on German understanding of the Tiger II's limitations. "We knew," Steiner said simply. "Intelligence officers knew. Many field commanders knew. The Tiger II's weaknesses weren't secret within professional military circles. They were painfully obvious to anyone who looked honestly at operational data." "Then why continue production?" Morrison asked. "Political pressure, institutional momentum, and desperation," Steiner replied. The Tiger II was prestigious. It featured prominently in propaganda. Admitting it was a strategic liability would mean admitting our entire approach to tank warfare was flawed. And by 1944, we were desperate. We needed to believe in wonder weapons that could reverse our fortunes. Steiner described briefings he had given to senior commanders. "I presented data showing that Allied tank production exceeded our capacity by factors of 20, 30, even 40 to 1 depending on the category. I showed that increasing individual tank quality couldn't compensate for this numerical disparity. I was told I was being defeatist." He pulled out a document he'd saved, a comparative analysis he'd prepared in late 1944. It compared German and Allied tank production, reliability rates, operational availability, and combat performance. The analysis concluded that Germany should focus on producing larger numbers of medium tanks rather than small numbers of heavy tanks. "This recommendation was rejected," Steiner said. "I was told that German engineering superiority would prevail. That one Tiger II was worth 10 Shermans, but it wasn't true. A Tiger II might defeat 10 Shermans in ideal conditions, but ideal conditions rarely existed, and America could replace 10 Shermans in the time it took us to repair one Tiger II." Morrison found Steiner's testimony particularly valuable because it came from within the German military establishment. This wasn't Allied propaganda. It was a German officer acknowledging his own side's failures. "What should Germany have done differently?" Morrison asked. Steiner considered carefully. "With perfect hindsight, we should have focused on the Panzer IV and Panther, produced them in much larger numbers, and accepted that we couldn't match Allied production capacity. We should have emphasized reliability and operational availability over maximum performance. The Tiger II was a magnificent tank defeated by arithmetic, by the simple mathematics of industrial production and strategic logistics." December 1945 brought the final phase of evaluation, analyzing how the Tiger II actually performed in combat compared to its design specifications. Morrison's team compiled combat reports from both German and Allied sources, interviewed combat veterans from both sides, and constructed detailed engagement analyses. The Tiger II's theoretical combat performance was impressive. Maximum engagement range against enemy tanks, 2,500 plus meters. Probability of penetrating frontal armor from enemy tank guns at typical combat ranges, 801,200 meters, less than 5%. Rate of fire, approximately 6 rounds per minute. Crew training, typically excellent, as Tiger II crews were selected from experienced tankers. But combat wasn't theoretical. Morrison's team analyzed 47 documented engagements involving Tiger IIs where sufficient records existed to reconstruct events. The findings were illuminating. Average engagement range, 680 meters, far shorter than the Tiger II's optimal range. Environmental factors, urban terrain, forests, hills, limited sightlines. Most combat occurred at ranges where the Tiger II's advantages were minimized. Average engagement duration, 12 minutes. Combat wasn't prolonged duels at long range, but short, chaotic encounters where the first shot mattered more than armor thickness. Primary cause of Tiger II losses in combat, not frontal penetration, 11% of losses, but side-rear hits, 42%, mechanical breakdown during engagement, 23%, crew abandonment due to tactical situation, 15%, and air attack, 9%. Average kill ratio, 3:8:1 in favor of Tiger IIs, impressive but far below the 10:1 or 20:1 ratios claimed in propaganda. Morrison found the mechanical breakdown statistics particularly significant. In nearly a quarter of engagements, Tiger IIs were lost not because they were defeated by enemy fire, but because they broke down during combat and couldn't be recovered. One engagement near Cologne in March 1945 was illustrative. 3 Tiger IIs engaged 7 American Sherman tanks in an urban environment. The Germans achieved first kills, destroying 2 Shermans quickly, but urban terrain forced close-range combat where the Tiger II's armor advantages were less significant. During maneuvering, 1 Tiger II's transmission failed. The crew abandoned it. A second Tiger II was hit from the side by a Sherman that had maneuvered into position using narrow streets. The Tiger II was too large to traverse. The third Tiger II destroyed 3 more Shermans before being disabled by infantry with bazookas. Final tally, 4 Shermans destroyed, 3 Tiger IIs lost. Kill ratio, 1:33:1 in favor of the Tiger IIs, but the strategic outcome favored the Allies. The position was taken, the route was opened, and American forces advanced. 4 Shermans were replaced within a week. 3 Tiger IIs were irreplaceable. Combat is complex, Morrison wrote in his analysis. The Tiger II wins most individual engagements it participates in, but winning engagements and achieving strategic objectives are different things. The Tiger II can dominate a particular piece of ground, but it can't dominate everywhere simultaneously, can't be rapidly redeployed, and can't sustain operations without extensive support. Morrison's evaluation included analysis of how Allied forces adapted to fighting Tiger IIs. He interviewed American, British, and Canadian tank crews who had encountered them. Lieutenant Robert Harrison, a Sherman commander who had fought in Northwest Europe, described the tactical evolution. "When we first encountered Tiger IIs, they were terrifying. Our 75 guns were useless against their frontal armor. Even the 76 struggled, but we adapted." Harrison described the adaptation process. "We learned not to engage frontally. Tiger IIs were slow, couldn't maneuver well in close terrain, and couldn't traverse quickly. We used mobility and numbers, engage from multiple directions simultaneously, force them to choose which threat to address, flank get side shots, use terrain, forests, urban areas, hills that limited their range advantage. British Lieutenant Colonel James Pemberton, who had commanded a regiment of Sherman Fireflies, Shermans equipped with the powerful British 17-pounder gun, added perspective. The Firefly could penetrate a Tiger II from the front at reasonable ranges, but even then we didn't take them on frontally if we could avoid it. Why risk it? Maneuver, concentrate force, engage from multiple angles. One Tiger II can't cover all directions simultaneously. Infantry cooperation proved decisive. Sergeant Michael Sullivan, an infantry squad leader, described combined arms tactics. Tiger IIs were vulnerable to infantry, especially in close terrain. Bazookas, sticky bombs, close assault. In Cologne, we knocked out 3 Tiger IIs with infantry attacks. They couldn't protect themselves in urban fighting, too big, too slow, limited visibility. Air power was another factor. Allied air superiority by 1944-1945 meant Tiger IIs faced constant threat from above. Armor that stopped tank guns offered little protection against 500-pound bombs or rocket attacks. German records showed that approximately 10–15% of Tiger II losses were attributed to air attack. The fundamental issue, Pemberton concluded, was that the Tiger II was designed for combat conditions that no longer existed by 1944. It was designed for open terrain, long-range duels, set-piece battles. The actual war was close quarters, fluid, multidimensional. The Tiger II was a specialist designed for conditions that rarely occurred. January 1946 marked the conclusion of Morrison's evaluation. He compiled his findings into a comprehensive report titled Technical and Tactical Evaluation of the German PZ KPFW VI OSF. B. Tiger II, Heavy Tank. The report ran to 847 pages, including appendices, photographs, and technical diagrams. The executive summary was direct. The Tiger II represents the ultimate expression of a tank design philosophy that prioritizes individual vehicle combat performance over operational effectiveness. It is the most heavily armored, hardest-hitting tank evaluated by this team. It is also one of the least practical tanks for modern, mobile warfare. The Tiger II's weaknesses: excessive weight, limited mobility, high fuel consumption, mechanical complexity, and maintenance intensity, are not minor flaws but fundamental limitations that severely constrain its operational utility. A Tiger II battalion at full strength and adequately supplied can dominate any tactical position it occupies. But achieving and maintaining these conditions in actual combat is extraordinarily difficult. Most significantly, the Tiger II's design requires resources: fuel, specialized parts, extensive maintenance, heavy transport, that Germany could not provide in sufficient quantity by 1944–1945. The tank was designed for an industrial and logistical situation that no longer existed, if it ever did. American tank development should learn from the Tiger II, specifically, what to avoid. The ideal tank is not the one with the thickest armor or the most powerful gun, but the one that can be produced in sufficient numbers, maintained in field conditions, supplied with adequate fuel and ammunition, and rapidly deployed to wherever combat occurs. The Sherman tank, despite its well-documented shortcomings in armor and armament, better embodies this philosophy. It could cross any bridge. It could operate 200+ kilometers from supply bases. It could be maintained by standard maintenance crews with standard tools. It could be produced in overwhelming numbers. These attributes, more than armor thickness or gun power, determine the war's outcome. Morrison included specific recommendations for American tank development. Prioritize strategic mobility over tactical invincibility. Weight must be carefully controlled. Any tank unable to cross standard bridges has severely limited utility. Design for operational availability. Reliability, ease of maintenance, and parts commonality matter more than maximum performance. Consider industrial production from the design phase. Tanks must be designed for mass production using available manufacturing techniques. Fuel efficiency is a combat parameter. Extended operational range provides strategic flexibility that armor thickness cannot. Logistics determines capability. The best tank is worthless if it cannot be supplied, maintained, or transported. Morrison concluded with an observation that summarized his team's findings. The Tiger II could accomplish things no Allied tank could accomplish. It could engage and destroy enemy armor at ranges beyond retaliation. It could withstand direct hits from weapons that would annihilate lighter tanks. In individual combat, it was often superior. But war is not decided by individual superiority. It is decided by sustained operational effectiveness across multiple dimensions: production, logistics, mobility, reliability, maintainability. In each of these dimensions, the Tiger II was severely limited. It was the ultimate tactical weapon that failed strategically. The bridge problem symbolizes this perfectly. A tank that cannot cross bridges cannot maneuver. A tank that cannot maneuver cannot be strategically effective regardless of its combat capabilities. The Tiger II was designed to dominate the battlefield it reached, but reaching the battlefield consistently and reliably proved beyond its capabilities. The Tiger II, evaluated at Aberdeen, eventually left the proving ground. After serving as a training tool for ordnance officers learning about foreign tank designs, it was transferred to the U.S. Army Ordnance Museum at Aberdeen, later Fort Lee, Virginia, where it remains on display today. American tank development in the post-war years reflected Morrison's recommendations. The M46, M47, M48, and M60 series maintained careful weight control. The M60 tank, which served as America's main battle tank through much of the Cold War, weighed approximately 52 tons fully loaded, heavy but manageable. It could cross standard military bridges. It was reliable. It could be maintained in field conditions. It could operate extended distances from supply bases. The lessons from the Tiger II evaluation influenced more than just tank design. They shaped American military doctrine about the balance between quality and quantity, between individual excellence and systemic effectiveness. The understanding that superior individual weapons could be strategically defeated by adequate weapons produced in overwhelming numbers became a cornerstone of American military-industrial policy. German engineers who worked on the Tiger II had mixed feelings about the design in retrospect. In post-war interviews, several acknowledged that the tank represented engineering ambition unconstrained by practical limitations. Heinrich Ernst Niepkamp, one of Germany's leading tank designers, reflected in 1948. "We built what we thought was the ultimate tank. We succeeded. It was ultimate, but ultimate in an impractical sense. We built a vehicle for the war we wished to fight, not the war we were actually fighting." The Tiger II remains a fascinating case study in weapon design, a reminder that the most powerful individual weapon is not necessarily the most effective weapon, that tactical superiority can be strategically irrelevant, and that the constraints of production, logistics, and operational sustainability matter more than maximum performance. The bridge test at Aberdeen symbolized all of this. The Tiger II sat there, 68 tons of German engineering, the most formidable tank gun of its era, armor that could defeat any tank weapon, and it couldn't safely cross a standard bridge. In that single limitation lay the story of its failure: too heavy to move, too complex to maintain, too expensive to produce, too demanding to supply. The ultimate tactical weapon that couldn't achieve strategic effectiveness. Captain Richard Morrison's report ended with a simple observation that summarized 6 months of evaluation. The Tiger II proves that making a tank bigger, heavier, and more powerful doesn't make it better if it can't get where it needs to go. The bridge problem wasn't a flaw. It was a metaphor.